Let us discuss commutator of momentum operators. Consider two finite translations. One is in x direction and another is in y direction. Let a particle be at a point A, and this will translate to another point C. This translation is in x direction. Okay, so this is a finite translation. So finite, it translate this particle, it shift this particle from one point to another in x direction, delta x dash in x direction, and from here to another point in y direction, and finally it reaches at point B, and this finite translation is delta y dash y cap. Okay, the same this particle actually shifting from A to B, and first we are doing the operation in x direction and then y direction. Let us do first let us shift into y direction, and then let us shift into x direction. So finally the particle reaches at the point B. These two operations are similar. In shifting from A to B, it does not matter whether we are going through the point C or through the point D. That is, it does not matter which operation we are doing first, whether delta x dash x cap or delta y dash y cap. We can discuss it in mathematically. Mathematically, if we are doing this operation first and later this one, that we can represent mathematically t of delta y dash y cap into t of delta x dash x cap equal to, using the property of translation operator, t of delta x dash x cap plus delta y dash y cap. And if you are going via the point D, then we can write t of delta x dash. Primarily we are doing operation in x direction, delta x dash x cap into t of delta y dash y cap equal to t of delta x dash x cap plus delta y dash y cap. It doesn't matter whether we are going in this way or this way. So right side of this equation 1 and 2 is same. Okay, and then we can subtract equation 2 from 1. That we will get t of delta y dash t of delta x dash minus t of delta x dash into x cap into t of delta y dash y cap equal to 0. Right side equal to 0 because this RHS of these two equations are similar. Okay, so the left side, this is actually, if we are taking this is A and this is B, then this is B, this is A, so AB minus BA, this is a commutator bracket of translation operator t of delta y dash and t of delta x dash, t of delta x dash. Okay, so the translation operator, in last class we have defined finite translation operator as, finite translation operator we have solved t of delta x dash in x direction, delta x dash in x direction as e raised to minus I px delta x dash divided by h cross. Okay, if it's translation operator of delta y dash, then we can write e raised to minus I py delta y dash divided by h cross, and the commutator of this 2. Okay, that's equal to 0. We can expand this commutation bracket, this terms, each of these terms. Okay, using this is e raised to in the form of e raised to minus x. This is also in the form of e raised to minus x. So we can expand this term as e raised to minus x equal to 1 minus x plus x squared divided by 2 factorial, etc. So each of these terms I have expand in the form of e raised to minus x, and I got 1 minus I py delta y dash divided by h cross minus, etc. And this also I have expand 1 minus I px delta x dash divided by h cross, etc. Okay, this is a comma because commutator of this term and this term. And then we are expanding this term again, that is 1 1. Okay, if you are the property of commutator bracket, if a plus b comma c plus d, we can define as a comma c plus a comma d commutator of a d plus I'm writing here, okay, there's no space, that's why a d commutator of plus commutator of b c plus commutator of b d. In this format we can define this is a property of commutator bracket, and I have expanded this commutator of these two terms like this, and we will get 1 1 minus 1 minus I px delta x divided by h cross plus, etc. because 1 comma 1, then 1 I px delta x dash by h cross, and then 1 comma px square delta x dash square divided by 2 h cross, etc. It's extending, and then taking the second term I py delta y divided by h cross comma 1, that is that represents that we are taking 1 the second term, and then etc. Then we are taking this term, and that is this term minus I py delta y dash divided by h cross comma 1 plus, etc. Okay, using this term, and like this we will expand this whole terms, and we are skipping the term with skipping second order terms, because in second order term this is a delta x dash square, here it's delta y dash square, and we will skip this all terms because it's negligible values, delta y dash square or delta x dash x dash square. The values of this are negligible because this is a fine, even if it's finite, this is very small values, so we can neglect that term, second order terms, and finally we will reach this is equal to this 1 1 equal to 0, because 1 1 commutator bracket 1 1 equal to 1 into 1 minus 1 into 1, that will be equal to 0. If anywhere constant comes, then commutator bracket will be equal to 0, because commutator brackets are defined as AB minus BA, so that's equal to 0. So finally, if you are skipping the second order terms and this terms we will get that is equal to 0. So finally, this approximately we can write I py delta y dash divided by h cross minus comma I px delta x dash divided by h cross. Okay, that is equal to minus delta x dash delta y dash divided by h bar square py px. These two terms need not write in order. Okay, because delta x dash into delta y dash equal to delta y dash into delta x dash. This is a finite translation. This is finite distances. This operators similar to infinitesimal distance or infinitesimal in infinitesimal translation operator we have learned dx dash equal to a number into an identity operator in some particular direction. Similar, this is also like this, so we don't need to write in order. So we can write delta x dash delta y dash divided by h bar square into py px plus delta x dash delta y dash divided by h bar square px py. So we can take these two terms common. And that will provide that is equal to delta x dash delta y dash divided by h bar square into py px minus px py, that is equal to minus delta x dash delta y dash divided by h bar square py px, that is equal to 0, because we have already this term is LHS of this equation, and RHS we have already seen that is equal to 0. So these terms are finite distances. Delta x dash and delta y dash are finite distances, and this h bar square is a constant, so we can understand the commutator of py px equal to 0, that is py px equal to 0. Okay, or generally we can write pi pj equal to 0. Pi pj equal to 0. That means px py or py pz or pz px all will become 0. That means whenever the generator of translation commutes, the corresponding group is said to be abelian. Okay, here it commutes, and whenever the generators of translations commute, the corresponding group is said to be abelian. So the momentum translation operators in 3 dimension used to commute, so this groups we can say that it's abelian. Okay, pi pj equal to 0, commutator of pi pj equal to 0 means that the measurement of momentum in one direction does not affect the measurement of momentum in another direction. That's the physical significance or physical meaning of this commutator of pi pj equal to 0. We got the relation commutator of pi pj equal to 0. That implies that px, py and pz are mutually compatible observables. Mutually compatible observables. We can therefore conceive a simultaneous eigencut of px, py and pz, and we can represent simultaneous eigencut p get momentum, this is the momentum get, that is equal to simultaneous eigencut of px dash, this is p dash, px dash, py dash, pz dash. Okay, that means if you are operating with px on p dash, we will get px dash, px dash, p dash. Okay, or operating with py on p dash, we will get py dash state p dash, or we are operating with pz on p dash, will give eigenvalue pz dash state p dash. So what will happen if an infinitesimal translation operator tx dash is operating on a momentum eigencut p dash? This is equal to 1 minus this infinitesimal translation operator we have learned earlier, 1 minus I p dot dx dash divided by h cross is operating on a momentum eigencut p dash, will provide 1 minus I p operating. Okay, this p operating on p dash will give I p dash, this is an eigenvalue p dash, ip dash dot dx dash divided by h cross state p dash. That's the momentum eigenkits remains the same if you are operating infinitesimal translation operator t of dx dash on momentum eigenkit p dash. And we can write the commutator of momentum and infinitesimal translation operator dx dash equal to 0, because p comma this term contains 1 minus I p dot dx dash divided by h cross. Okay, this term, this also in terms of, this is also this momentum, and this also in terms of momentum, this momentum operator. So earlier we have proved that pi pj, commutator of pi pj equal to 0. The whole terms contain this kind of commutator brackets, and this is also equal to 0. Okay. Finally, we deduce the commutator relations, that is xi xj equal to 0, pi pj equal to 0, xi pj equal to ih cross delta ij. These are known as the canonical commutation relations or fundamental commutation relations. Okay, and there are relations between Poisson brackets and commutators. Poisson brackets actually we have learned in classical mechanics, and there is a relation between Poisson brackets and quantum mechanical commutators. That is Poisson bracket that is actually equal to, or we cannot say equal, but in quantum mechanics we can represent that Poisson brackets as commutators divided by ih cross. If you are taking commutator of or Poisson bracket of position and momentum xi pj, that is equal to delta ij. That means in quantum mechanics this is equal to ih cross delta ij. So Poisson brackets in classical mechanics equal to commutator of position and momentum divided by ih cross. So as an example we can show this one, and I am introducing here some properties of Poisson brackets and quantum mechanical commutator. These properties are similar in classical mechanics. The properties of Poisson brackets, and in quantum mechanics the properties of commutators are same or similar. So I am introducing here that is commutator, Poisson brackets of AA, or commutator of AA equal to 0 and AB equal to minus BA, AC equal to 0, C is just a number. If C is just a number, commutator of AC equal to 0, or Poisson brackets of AC equal to 0. And this relations you have to note. This is very important relation. These are very important relations. And finally, another relation, the commutator of ABC plus BCA plus CAB, it is in cyclic format, equal to 0, and this identity is known as Jacobi identity. Jacobi identity. All right.